Okay, so let me minimize the chat for now and remove this guy here. I'll put it over here. Okay, so we have session 9, which is streams. And when I say the word streams, what comes to your minds, guys?
I don't know. I guess I think I've seen the concept kind of before, just like if like data flowing. I guess that's what comes to mind, like from a file or something.
Well, even when you go to, if we went to, actually, let's minimize this guy. Let's do it over here. Even if you go to T-Mobile, and usually like they even advertise this, and I'm using T-Mobile not as an endorsement, it's just like I've seen it on the website, that sometimes it would be like, see, get up to 4K of video streaming. So the concept streaming, in reality, a lot of it comes because the way that architecturally all these things were set up, and this is, like now it has, just like the word app has become part of our vocabulary, streaming has become part of our vocabulary because of this, because there's the concept of streams as data is coming in. Let me just switch to the so as we let me start a new journal thingy. Just I want to draw something. Let me just delete this. Why is it not letting me delete it? Well, I don't know what's going on. My daughter's drawings. Oh, this is yeah, my daughter has a very specific way of drawing that it's a little funky. New page. I have no clue. Yeah, this one says that it's 138 pages. Yeah, this should be fine. I don't get it. I'm doing something wrong in here. Anyway, you know what? I'm going to recycle this guy. So the concept of streaming, and this is why I wanted to draw, is because imagine that we have a capability of seeing this much data, right? This much data is what we can see. But what would happen if we are sending this much data? The thing about streaming is that we can grab chunks of data and send just that data and be able to essentially just slide the window to keep seeing the data that we want. So that's essentially what is happening on streaming. If from a visibility perspective, and even all these even T-Mobile thing that I was showing you, it says to stream it to 4K data, which is already quite big. And also, like, say that we're streaming a movie, and let's think of a movie that's really long. I think Avatar was really long. Let's see, Avatar runtime, 2 hours and 42 minutes. Can you imagine running 2 hours and 42 minutes at 4K, surround 5.1 sound? This is a lot of data to send it to over the wire. And when you are starting to stream, like when you get on Netflix, they have nailed it down that the user experience of Netflix is that essentially as you are navigating and you get the title of the movie that you're going to just browse, big title, they already have the movie playing here. And if for whatever reason within 10 seconds you press nothing, this expands and takes over the full thing. The point that I'm trying to make is that within a few seconds, you're starting to get data immediately. And most likely, whatever device that you have, I mean, let's look at, for example, let's just assume a Roku stick. Roku stick specs. The hardware specifications for a Roku stick is 512 of RAM, the Roku Express. And let's go for this one that it's 1 gig of RAM, which is not a lot by these days standards. For example, some of these classes, when I've edited them online and stuff like that, they're about easily 500 gigs, and I'm doing only HD, and it's not surround 5.1, meaning that there's 5 channels of audio. So if you want to start streaming something, the secret of streaming is that you can just grab slices of windows at the time of that entire data set. And as you are moving, you're visualizing these parts, like A, B, C, D, E, F, etc. You're only visualizing whatever you can handle and then moving that window and sliding it over. So that way, eventually, you're going to be on that last window reading the last few values. That is essentially the concept of streaming in the way that Java allowed it to, Java, that's one of the biggest reasons why Java is the language of big data. Yes, languages like Python is the language of data science and analytics, but Java is the language of big data. And if you don't believe me, then go and ask Google, because we use that all over the place, and it has been the thing that has allowed to the internet to process all that data. So again, the concept of streaming comes from Java in this sense. Of course, there's computer science and computer theory behind it, but it became popular because the developers were just like, hey, why don't we use IO streams for this kind of stuff? And just like it is on a river, like because stream is essentially like a river. And if you are standing in front of a river and you want to grab a little bit of water, you don't go to the very beginning. You just go in and grab whatever is in front of you. It is essentially the same thing with streaming. Do I see you wanting to say something, Josh? No? Okay.
It's kind of like the transformation in thinking from the year 2000 to the year 2010, where everything was, you download it, so you have all of the data sitting in your lap and you just press play for multimedia. And then 2010 to 2020 is basically the decade where that completely and utterly took over, to the point where the size of a hard drive really doesn't matter anymore. And that's why Chromebooks are out and popular, and basically Chromebooks are
exactly
that transformation.
100%. Like if you notice, for example, an iPhone, how many years has it been since the iPhone has had maximum 512 gigs of storage? And do you need more? A lot of people know, like, you just get your iCloud plan and it uploads the things into the cloud. And yes, that transformation happened from the 2000 to 2010, from going into from your own data center or on-prem to the cloud. But all those concepts came in from slightly before. Java enabled that. Java was developed in the late 90s. And in many ways, these days, Java is playing catch up. Don't get me wrong. Like there's plenty of things that are wrong with Java, but that transition from I download my MP3s and I have them on my computer, and right now I just pay for a subscription of Spotify and I get whatever I want because I don't need to have it. I'm going to be streaming. And not only that, it also allows you, or like, you know, if we went to YouTube, and this is just, you know, generic YouTube page, where I don't know what this is showing here, but you know, let's, oh wow, Mark Rober already made it to the, well, the guy has 22 million views on his videos. He's um I could I can jump, skip ads. See, I just went to T-Mobile and it started but I can jump into any portion of the video, and I did not need to have the video downloaded to my computer. I just start streaming from that point on. And it just magically, since, you know, within milliseconds, sends that data from that point without having to download it. At the very least, you know, I'm gonna sound dated, but when in my time, you would have to download all that, and a lot of that was through dial-up, and you know, it was boring to download all that and just leave the phone line locked. So that's the concept of streaming. Also, streaming not only applies to reading data, it also applies to writing data. You can write data to a stream, and believe it or not, anything that you're doing on Facebook, anything that is happening on Twitter, is being logged in a streaming system. You're sending a bunch of events, and you have a central system. And this is you know, this is literally what happens in big data systems. You have an architecture that it's based on streaming. Oh, come on. Where you have a client. You have, actually, you can have several clients. You can have another client, and that data is sending it to just a server that it's absorbing everything, adding it to a queue, and then you have a streaming process like Kafka, which is also written in Java, Apache Kafka, that it's going to absorb it. So actually, you know, we don't send it to a queue. Kafka has its own queue. So you have a service that it's literally listening for data and sending it to something like Apache Kafka. And then you have another system that is consuming it. So whereas it goes into a database after that point or whatever, that's how you consume it. But Kafka is allowing that stream and essentially all that buffering from the other way around, where people are writing at in a streaming fashion and feeding in all these big data models. I hope this is not boring to you guys.
So wait, Juan.
Yeah.
So what is, I mean, just to get another person, like, well, what exactly is buffering then?
Excellent question. So let's get to that in a second, because this is all tied together.
Okay.
So streaming works if you have all this memory. You know, like somehow, you know, you might not need to have all this memory, but buffering means that I'm going to be sending you a bigger chunk of data than what you can consume right now. So that way you have it available if you decide to use it. That's why when you are using Netflix or whatever, you get these, you know, you don't get it anymore because now networks have been, and all the systems have gone to like microseconds of processing of that data. But before, you would see buffering, and buffering would be like, I'm going to send you as much information as I can so that you have a buffer and you can start consuming that data. So hopefully by the end of that, or by the time that you are done to the first buffer that I send you another buffer, and you can see it being consumed. You know, like a movie is being consumed at 24 frames per second. if I send you 3,000 frames already as a buffer, you're never going to catch up, and you're going to feel like there's a smooth experience. It's essentially, that YouTube thing that I was telling you. Like, you can see, let's go back to YouTube just to explain this part, because buffering, we're going to really talk about that part here. So let's go back again into the marker over.
Doesn't buffering basically create a constant where if your machine cannot keep up with that constant, you have this idea of buffering? But if you can keep up with that constant, as you said, the 24 frames per second, you'll never have to worry about buffering.
Buffering happens regardless.
Oh.
Buffering happens regardless. The difference is that in one side you notice it, and in the other you don't. If you're in a slow network connection, you're going to run out of that buffer, and then there's going to be code behind that. It's going to be, when we reach that exception that you don't have enough, the only thing that I'm going to print is that I'm buffering. But if I were when, come on, skip trial, you're going to notice here on the timeline, there's two colors. There's a red, there's a white, and then there's wherever I'm putting the cursor. So you see how the cursor, like around here, it becomes more evident. It's downloading everything. You see that this whitish color by my pointer?
Yeah.
Okay, that's the buffer. If for whatever reason I consume that buffer before it gets there, right now it's just too fast and it starts downloading immediately. But before, when there were not like great connections, great internet connections or something, it would wait for that communication to come in, and then it would say buffering. Does that make sense?
Yeah. So what happens if you or what is going on when you skipping very far ahead though? Like, say you skip way ahead of the buffer.
Yeah. So the buffer is all the way down here, and I'm going to skip all the way here. So what happens is that then a new request is going to be sent to the server, and then it will say, start sending me the video from 11:07, which is the, let me hide this, and then say, okay, 9:59. And then that little transition there was the request being sent to the server, and then the server sending back the first buffer from that moment. But rather than, that little jump outside of the buffer, in the buffer, it's immediate. Inside of the buffer is immediate. But when it's like far, you saw it, how it paused for a second, and then it immediately did it. That's because it had not caught that. So if my internet was slow, which I think I can actually pretend it in here. And this is going to be a mistake because it's going to, but there's ways to troubleshoot a connection. I'm going off topic, but you guys are interested in this. There's a way to emulate like going through like a 3G network. And if I were to buffer, it would pretend to be slower, and it would take a little bit longer to start getting that data.
So what happens if you, I guess, what is going on if you go backwards? Does it still have the buffer, or?
Yeah, no, it just sends a new request, like because the buffer, at the end of the day, for example, this laptop, let's look at it. This laptop has 16 gigs of RAM. Pretty okay for, but it's not. I mean, it's not a huge amount of RAM. And I'm sure that this video probably has, 5 gigs of space. But this computer is not using 16 gigs of RAM just for this video. It has Chrome open, it has IntelliJ open, it has QuickTime open, it has Safari open, it has Zoom open. So those 16 gigs have to be shared across everything that I'm doing. The player here is going to free up some of the memory. Once you're at this point, it doesn't need the data here on the beginning. It's just for user experience, it puts it in red as a okay, you already saw that, or you're not interested. But if I were to go back again to the beginning, you saw it blinked again, and it went into, because buffering only is a tiny bit. And that's where I tie everything back into our class, because we're going to have some buffer mechanisms of reading data, because you cannot be reading character by character. You can read chunks and chunks and chunks. What is faster? Like if I gave you a book right now, what is faster for you to read? Word by word or letter by letter?
Word by word.
And what makes it easier for you to comprehend? Word by word or letter by letter?
Also word by word.
Word by word. The word is your buffer. Now, if you're a fast reader, you might actually see 2 to 3 words at the same time, because that's actually how fast, when you're learning how to read fast, anybody that has learned that mechanism is just pop, 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 pop. Even in some cases, like they've done tests of somebody that is reading, and they discourage as much movement of your eyes going in this direction. They want just pack, 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 pack. Like it's a lot faster because you're reading more words, so you extend your buffer. Same thing happens here with a computer.
So what is the buffer limited by? Like the RAM, or is it just whatever the code tells it to?
It is whatever the code tells it to, and if the code is smart enough, then it could determine a chunk of buffer to utilize. Now, just to maybe understand buffering a little bit. So technically, everything in the computer, we know that there's two types of data, right? We've talked about this before, where there is data that is going to be consumed by the computer, and there's data that is going to be consumed by humans. And technically, everything at the end of the day is consumed by humans. But if it's a text file, like the source file of a computer, it is designed and optimized for human consumption in its source format. If we were in YouTube, all of this is binary data. All of this is just binary data that it's being sent, describing each pixel. If this pixel is white or blue, or the t-shirt being blue here, and some compression algorithms and whatnot. So Java allows us to have 2 categories of readers, whereas one is the binary one, which is capable of reading everything, and then the other one is the text, which is optimized for reading a character or some text and stuff. And just like in exception, that we have exceptions that are errors and exceptions, that it's just a naming convention on the class name, where error is outside of the scope of what your program can handle or should fix, and the other one, exception, is that you can recover from your program itself. Same thing here. We have a naming convention. We have the naming convention of whether it's text or binary. If it is text, there's a suffix for all the classes, that it's writer or reader. That is a tell-all that if you want to use text directly, your class is going to end with writer or reader. If it is binary, you're going to be using input stream or output streams. So that's just naming convention. The mechanisms are going to be the same, similar, and so much that in this chart here, I'm showing you analog classes side by side. So for example, buffered input stream, that one is built into the language. This goes back to buffering, where you let Java handle the buffer size and all the possible buffer. You forget about the buffer itself. You don't have to write that code. Java is giving that to you for free. But if you use buffered input stream and buffer reader is going to be text. Buffered input stream is going to be a YouTube video, a Spotify song, a Netflix movie. Now,
can you use the byte stream? So you can't use the byte stream to do text at all?
No, you can, because at the end of the day, text is binary.
Yeah.
But the other one is just optimized so that you don't have to convert it. It's just saving you the extra step. And all these classes are analogous to each other. Like buffered output stream is analogous to buffer writer. You know, the only thing that it's output stream and writer are telling you who's using what. Input stream is byte array. Input stream is just, you know, as handling it as an array rather than as a buffer. And a buffer could be dynamic. An array is just a cheap way of creating a buffer. And it's fixed, as you guys remember that arrays are fixed in size. Char array reader, you know, it's analogous classes. Anyway, so far I've spoken a lot and I have not asked for numbers. Oh, and I see that I have the Irishman. Which one was the Irishman, George?
That's for the movie durations, 3.5.
Oh yeah, the Irishman. Yeah, that is a long movie. That's true. Okay, Sareth told me that he's at a 9. Brandon is at a 9. George is at a wow. Either you guys are really generous, or I am doing my job, and I'd like to think that it's the latter one. So, anyway, then let's move on this. So, because all these reading mechanisms, there are, you know, there's a lot of classes depending on what you want to do and how you want to handle it. But there's a common set of API across all of them that do have a common set of interfaces that API, probably that would be the proper term, that either close, read, skip, you know, open. I put close the source and close the stream. It was supposed to be open, read, skip, close, and write. You know, just basic operations. It kind of tries to have everything as uniform as possible, so that way it's easier to remember. And if you find a new input stream or an output stream, they follow the same mechanism. Now you can see that how some of these, and actually I even have the theory. Let's do it in Chrome, because if we get buffered input stream in Java, likely all this input stream is where all these methods are defined: read, write, read, reset, skip. And it's most likely it's an abstract class. So this is, see how we're tying in the things that you've learned. An abstract class is incomplete. That means that it's going to lead, it's going to, you know, the read mechanism, the read method is abstract. It's going to allow each one of the classes, the subclasses, to determine how it reads that data, because reading from network is not the same as reading from a file or reading from any other mechanism. So this thing just permits the reading and to be defined by a subclass. Sweet. I'm moving fast enough, because what I want, I mean, these are not too big topics. So I want to, since technically today is our last class, I want to pack as much of the 2 classes today, the 9 and 10 sessions. Oh, I remember, yes. So they removed that last session, but I still have the slides. And usually in this last session, it's when I pack them and make them into a bigger session, so that way you guys get the same content than before.
Do we still have the same amount of time to finish the final project?
Yes, and that's exactly why I, you know, I was concerned with like that I do have to stick to today being the last class, because I have to turn in the final projects by maybe end of next week. And if we had another session next week, I would really put you in trouble for like giving the final project, and UCLA would close the window that I have to submit classes. Anyway, if it was up to me, I would continue doing this because I enjoy talking to you guys. But unfortunately, there's limits. Cool. So let's talk about how do we, you know what, before we go into chaining streams, well, we can chain one stream to another stream to another stream to another stream. And that's how we can convert data. You know, at some point here, we are going to chain from reading from the UCLA extension all the way to saving it as a zip file by chaining streams together. But for now, let's try to do this exercise. I would like you guys, first of all, to let me give you 2 minutes, no, 3 minutes for you guys to copy this into, let's do one thing, actually. I'm going to give you 2 minutes, no, 3 minutes. I want you guys to create the simple URL reader. You can even copy this, and I would like you to copy the other one into another file. Copy both of those and run them. And I would like one of you in 3 minutes, no, 5 minutes. Let's do 5 minutes to explain to me what's the difference between using buffer reader and creating a fake buffer using an array. I would like you guys to run it, and then you guys are going to explain it to me. Okay, let me put in the timer. 5 minutes. And I'll let you guys copy that from the slides. And then in 5 minutes, let's get that that difference. Okay, what is the difference between buffer reader and the fake buffer by using an array? Okie doke. The countdown went to 0. So who was able to determine the difference between both? Anybody? Who's gonna? Who was able to get it? Let's see. Jose, were you able to get it?
Actually, I'm still typing it out, so I haven't even read the message.
Okay.
Yeah.
Was
Yeah, I'm
anybody?
also typing it.
Okay, so how about this then? How about then? Well, I'm gonna. Maybe in the interest of time, and to I'm going to show you. There's 2 different reading methods here, right? And I'm going to put them side by side. Split right. Okay. Okay, so by the way, are you guys able to see yourselves on Zoom or not? Yeah. Okay. That way I can leave the window there. Okay. So basically these 2 are doing exactly the same, but if I run the one on the right, you are going to notice that technically both of them are reading the same content. And if I pass these to a browser, it would probably be the same. But you can see how the buffer, it was always 100 characters, regardless of, like, I actually bet you that if I put this into Visual Studio Code, just as a random file, every line is 100 characters, even if it has a new line written to it. Even this first one is 100 characters long. I bet you that these, if I remove these guys, is basically those 100 characters. These two lines actually ended up having 2 extra characters or 3 extra characters, which is these two, which was the hidden character here and the hidden character here. But at the end of the day, every line is 100 characters. Even if they are a little bit smaller, these might be all into one, piled into one. But the buffer is just limited. Doesn't necessarily change much at the end because we were able to read the entire page, but the buffer is limited. Here, the buffer is a little bit smarter when we use the buffered reader class. Java is going to, there's lines that are gnarly and go really, really, really long, like this JavaScript one. You can see this JavaScript is a single one-liner thing. And there's other parts that in the code that you're going to see that type of thing. So long story short, we're using in both situations readers, we're reading text, but in one case we are limiting to 100 characters. In the other one, we're using the buffer reader, which is going to dynamically allocate it as best as it thinks it is happening there. That said, then let's probably get some numbers about the differences between these two files. Awesome. Okay, great. So everybody's at a 9. So then let's do our break. And then when we come back, I am going to have, rather than typing it directly into the class, I'm going to have it typed. And I think that the code is actually uploaded. So we're not really missing much, but in the interest of time, so that way I can review generics. I'm going to show you how we chain buffer, reading a buffer similar to here, like we're reading an input stream reader. We're getting the stream from the address. Then here we're chaining it to an input stream reader. And then we're passing that to a buffer stream reader. Well, what would happen if we grab that output, that input, and then send it to an output and piped it? And not only save it to a file, but save it compressed to a file. So we're gonna see that then right after the break. And I'll see you guys here at in 20 minutes. Sounds good? Okie doke. So before we continue, I'm going to give you a little bit of an explanation of what is going to happen. And this is something incredibly common in requests in HTTPS. Well, hang on. So the internet still takes advantage of, we don't have infinite bandwidth. But it tries to make the best attention. The internet tries to make the best experience for everyone, regardless of the connection capability. So one of the really most common things, just because it's really cheap, let me just hide everybody here for a sec. And if I go and look at the main document, we can see that, first of all, this document, it said that it took 162 milliseconds to download, and that the size was 14.3 kilobytes. When we look at the details of such document, we see that, where is this? That the response, Where's the response? Well, the response headers. Okay. So it is saying that the content is encoded as a gzip file. So that means that it compresses them into this really common compression algorithm. And because it is compressed, that means that we are actually, I think there's more. Remote address response content length. Okay. Our UCLA extension website, and I'm just going to shift reload it to make sure that we are re-downloading it. You're going to see that the main page, this index here, which is the contents of the main thing, you know. Oh no, this is not it. This is not it. Let's just say that this is, we're gonna try to find out which one is XHR. No, I need the actual slash page. Which one is the first one? Let's just shift refresh it again. Oh, crapola. If I use a key, hang on. Okay, so the network tab, this guy here. Okay, so this guy, when we close this guy, it says that usually when it's compressed, it is connection, keep alive, modified waterfall, scheme domain, remote address. What I'm trying to find out is the difference of the downloaded file versus what it was compressed, but for some reason it's not showing. Content length is 22 kilobytes. Well, let's actually run the code that we have. So let me explain to you what we're going to do. This code here is going to download the website UCLA extension. It's going to capture this new URL. It's going to put it through an input stream reader, and it's going to open that stream reader. It's reading it as text. It buffers, reads it in, and then declares where it's going to write it. And you can see in an interesting way, if we have these thing, we're declaring things on the input. We're declaring them from left to right: input stream reader, buffer reader. And on the output, we are declaring them from right to left. So we have the file output, the gzip, and the buffered output stream. File output, gzip, buffered output stream. That's essentially how we're declaring them. Essentially, from the outsides to the center. And what we, in this particular case, we're saying, okay, we're gonna create a new output stream that it's gonna write to gzip file. Then we are going to grab, well, if we're reading it from top to bottom, you know, we're creating a buffered output stream that it's connected to the buffer input stream reader and putting it side to side. It's this guy here and this guy here. It's this guy here and this guy here. Those are the centers. Then that output is going to send everything to the gzip output, which is this guy is going to grab that stream and compress that data. And then it's going to send that to the file output stream, which is this guy, and then save it as a file. So essentially, the variable declaration did happen from the outsides to the insides, but we needed that so that way we can connect all the inputs to the proper outputs. Once we declare all these variables, then we start reading the input stream reader. So we have these line, input stream, read line, different than null. We read that, convert it to bytes, and then now we write it. Here's where we do the conversion from text to binary. So we read that line, get those bytes, and write them out, and write also a new line to like essentially write each line as we are reading it, because we are reading a new line, then we're writing the text, and then we're also writing, essentially these two lines is the equivalent of out.write line, but you know, the write doesn't have write line, so we fake it this way. And then we close both the input buffer, which is this guy here, and we close both buffers, and both buffers communicate upstream or outwards. And I'm talking about outwards because it goes from here to here and here to here to close the stream and then save everything and then tell everything to be processed. So when we run it, it's going to show like if nothing had happened, but you're going to see a file appear right here as soon as it finishes running. And that file is a compressed UCLA extension source file. So actually, I don't want to launch a terminal. Yeah, terminal. Oh man, I might have messed up something or whatever. As we are running things here, we can actually see that the UCLAX HTML.gzip has 22. Let's even read it in human. Has 22K of content that is compressed, and it made it into 22K kilobytes, which is a 22368. When we look at here, and actually we can even see, it's essentially this content length. This is the difference in between these 300 bytes is probably the header that it sent as a response, because we're not capturing the header, like essentially this data. This data is the extra information, but and then uncompressed is going to be, you know, in this particular case, there's not that much gain, but in some other documents there is. Like sometimes you see like 10 bytes and then it's like 200 kilobytes or something. So when we uncompress it, it's going to say that it's, you know, if we gunzip UCLA extension, now we're going to see that this file uncompressed correctly. Actually, no, it did gain some. I don't know why it's, what would be the field right now. I don't remember exactly. Do I see it here? A way to see the total size of the file? No, I don't find it. Anyway, if we make it read in human readable terms, you know, we downloaded 22 kilobytes from the internet versus 109 kilobytes that it is uncompressed. And we see the file, you know, it's the HTML of the UCLA extension website. So that is basically how we share, how we would share, not share, how we would chain input streams and output streams. Okay. All right. Let's probably then get some numbers about this little exercise so that way we can go into generics. Sorry that I'm flying through this. I just want to make sure, you know, technically there's 9, but I named 9 sessions. I want you to get 10. Okay, George and Jose are at 9. Let's see what Brandon, Josh, and Sareth. Oh, everybody's at 9. Okay. Sounds good. Then let's see if there's any other things. Okay, random access files is just basically the easiest explanation that I can find for this is if we were going to compare files to books. If anybody of you guys used a dictionary, a traditional dictionary or the yellow pages or something like that, where basically you can just open it up in whatever page and it makes sense to you. That is a great analogy for a random access file. You cannot grab a novel and then start reading in the middle and make everything sense, because in reality, you would, in order for you to understand it, you need to go to the beginning and read it sequentially. But there are certain books that you can actually read from wherever and it would actually make sense. Perfect example of a random access file would be this, where I can jump into any new section and I can just start reading that file, and I don't need to read it from the beginning, because wherever it is, I am able to make context out of that. And that's the beauty of random access files. I can just either, rather than just following an order, I can just be whatever I can read it and make sense of it. That's like the simplest, super washed down version, but I think it's just good enough for us to understand that concept. Now, why are those relevant to this? Well, some of the common methods, actually, you saw this skip mechanism, and that skip mechanism allows you to just jump from the beginning till the end of that. To one part of another of that file. So you can go, from 3/4 in to the middle, and then continue reading, and then going back to the beginning and jump from one side to another of the file. Okie doke. Regarding streams, I think I probably answered all your questions, but if there's any questions, just let me know. Okay, so then let's jump into our last topic. Oh, and I left this thing that says streams here, sorry. Okay, let's talk about generics, and I'm gonna talk about generics in a higher level. We re-review some of these in Java too, but what are generics? You probably saw that when you were, let's go this guy here, and if we do hash table API Java, and if we look at the API, you probably saw this kind of notation. Did you guys notice that notation when you were looking at the hash table? Yeah. Okay, what do you guys think that is for?
Well, I know when we were doing the link list, I knew that was sort of a beacon to not use it, because we were trying to create our own, and that was the symbol for something that came with Java, and that's the point of the homework assignment, was to create our own as opposed to using the innate situation.
Yeah, actually, I'm glad that you remember the linked list, because the linked list is actually where we're going back to, and probably that was everybody's favorite assignment. So let's go back then to that linked list and start reviewing the use case of why generics are important. So if you guys remember, a linked list is a list that has two properties: a value that it stores and a pointer to the next element on the list. So we have next and value, and value and value and next, all the way to the point that that next pointer points at null. So let's assume that you guys now you're fancy programmers and you write this linked list for this job that you got and everything, and they say, you know what, remember the linked list that you wrote 6 months ago? It's great, customers love it, it's amazing, But there's one thing. Right now, we only support strings as the value that we're holding. I was thinking we already have all that code. What if we supported dates as well? You know, you could store a date and it has like a linked list to a next date. You know, the use case for this would be we are trying to write a calendar of US holidays and we want to have them in a linked list format. You're like, oh, sure, that makes sense. So you grab your file where you're storing your linked list, and then you're going to duplicate it. How was it duplication here? And you duplicate it, and then you decide to, you know, make one. This one is date, and this one is string. Okay, now I have two source codes. Cool. Then 6 months later, they will come back and say, man, that linked list with Java saved the quarter, sales are through the roof, but our customers are now asking us to do a linked list of calendars. So, you know, do you think we can do it? Sure. Then you go ahead and copy the same linked list, but now you have one that it's a calendar. And so on. You know, let's assume that you added a couple more formats like this. And now you have, you know, help me think of something else, an int and a long, and I'm using the capital versions of that. Did I talk to you guys about those? The wrappers around the primitives? I think I did.
Yeah.
And so on. You know, we created a bunch, but guess what? We found a bug, and that bug is represented by this little blue dot. And we go ahead and start patching that bug all over the place. Well, you know, that was painful. We had to patch 6 files with the same bug and test it all. And man, I wish there was a better way. Okay, well, then we found another bug. Okay, well, now let's patch that bug. And oh, another bug. Okay, well, let's just patch him. Let's just patch him. It's okay. And then we found ourselves in a situation where 2 of those bugs were not patched in 2 classes. You can see here, this guy doesn't have the yellow, and this one doesn't have that light green. So now we have a problem because all of our source code essentially forked to the point that then, you know, this has, it would have been nice if we would have rewritten that and handled it in one single pass and make it, you know, scalable from a code perspective. So this is where generics come in. Generics are basically a live search and replace that happens from the compiler. What does that mean? Well, let me rewrite the linked list real quick. So we have my linked list. And we had something like this where we had string name and my linked list next. And if we have public my linked list, well, let's not leave it with a constructor. Let's public void add. Oh no, public my linked list add, and you know, we're recreating this. We have my linked list pointer equals this, while pointer dot next is different than null. Then pointer dot next. And then we say my linked list new or node equals new my linked list, and we pass the name, and then pointer dot next equals node return node, and we're going to add the constructor, which is public my linked list, and we do string name. This is basically what what I gave you last time, where name equals name, and that's it, right? This is basically that pointer. So how would we then go and convert this into a generic? Very simple. We use this notation, and we say what we're going to do search and replace with. So for example, we're going to name this data type replace me, and I'm just naming it replace me because I want to make it evident. And now everywhere where I have this string, I'm going to say replace me. And just for cleanness of the code, I'm going to refactor this rename, and we're going to say value. Yeah, parameter name, everything now it's named value. Okay, so now I have a live search and replace that whenever I then go ahead and do main, my linked list, and we say date, and then my LL equals new my linked list date. And if I pass a string, because there's a live search and replace, the compiler will not allow me to pass that string. So in order for me to make it valid, I would have to do new date. But if I duplicate the code and the only thing that I change is string, I'm naming it my linked list 2. This my new date argument won't make sense. Now I have to comply to it, and I would say string. So you see how it is enforcing the data type that it's going to receive, because I am using this value that it's essentially doing a live search and replace. As I am saying, this linked list is going to have a date, and this string will have a string. I did not have to recopy the source code as that cheap example that I was using. I did not have to reinvent the wheel. All I had to do is to change my original file to be able to accept anything I want, and the compiler will assist me in keeping such values consistent. Does this make sense? Am I explaining myself correctly? So to understand if I am not saying nonsense, why don't we, oh, Sareth, good job, key value, yes. Good job. Okay, and that was the key and V, but essentially on the my linked list, on the linked list in here, oh, this one here, this is where we're going to define what is the data type that we're going to use for the key, and what is the data type that we're going to use for the value. So technically, we were going to do a linked list, a regular one, saying linked or hash table. And we can say string comma date equals ht equals new hash table string comma date. And now you can see that I am going to constrain this instance, only this instance of the hash table, to be a string pointing to a date, because it has two values. But you can see now because of the way that this is defined with k comma v, it's two values that it's replacing. You can chain as many as you want, and you can make the generics to utilize as many as long as you just repeat them via commas. Okay, let me then understand your understanding. So let's get some numbers for these guys.
Juan, is there a way to like restrict it to only using some like type or something like that? Or is that just like write the whole thing as a string?
Well,
Like,
here, yeah, so you can, this is the beauty of inheritance. You can put a superclass on that. And actually, let's even talk about that. Yeah, it's sometimes somebody's gonna think that Brandon has a script and he's going because his questions are like essentially like, great question. Let's go into the next slide. But I promise you, Brandon doesn't have a script. Let's talk about the generic of the considerations. They don't work with primitives. They only work with certain types of objects. And actually, if you do not specify anything, the default data type is object that it admits. So essentially, you're just making it generic for everything. But you can narrow it down by bounding it to saying, for example, if you want to, if say I want to just, you know, use a wildcard to like reduce at something like, you know, T extends superclass, I can say, well, replace me extends number. And what is a number class? Where the number class is the superclass for all the other, now you see like these went red because these classes don't extend the number class. Things that extend the number class are long or integer, essentially those wrappers of the primitives.
Okay, gotcha.
And now, obviously now these values are, you know, I can put like a 0 here and another 0. I don't know why it's not autoboxing here. Let's see what the compiler says. Oh, int. So I can do 0L, and now it converts it into that. But you can see, you saw that, you know, this makes it a little bit more generic. It makes the generic more specific.
Yeah.
So you can play with how specific you want to go, whether you want to go like super high and just extends from number, or going super low and extends from anything, you know, depending on your the level of specificity that you want to do. Okay, questions so far? We can use generics on methods by also, you know, using, if we use that as a data type. So for example, here I could have said like public replace me get value and say return value. Oh, what is this one? Return type required. Why did it not?
Does value have to be the same type as?
No, invalid method declaration with return type required. Let's see if I replace this for say log, just as a. Now this one is saying that. Ah, no, actually there it is. This is how we do it. We once we declare it up here, we don't need to be putting the greater than, lesser than. You can pass it as an argument. You can pass it as an attribute. Now, then there we get into a point where we have, well, before I jump into a different subtopic of this. Let me just make sure that I am. You're gonna use them on interfaces as a way to, like, you know, make things a little bit more versatile. Things to keep in mind, you know, it's easy to have ambiguity, especially when something is not defined. So just keep that in mind. You know, static members are not allowed with these type of generics. And why would static members not be allowed? Like I said, this is like a dynamic search and replace. So it becomes a dynamic search and replace at runtime of instantiation of a class. And because the classes, static members are shared across all classes that have been created, a generic won't work in those situations because, again, it's only upon instantiation of that class. Cannot extend throwable, and the overloading cannot be ambiguous. And that is, the overloading can be ambiguous. Also, it's something to watch out for, especially because overloading relies upon the signature not being the same. So if the signature is the same depending on the values, then you are essentially making things more complicated for you. Okie doke. These wildcards and bounds, I want to just cover this parameter one because this is interesting. What happens the moment if you have a hash table, like you're passing a hash table, like HT wrapper, right? And we have hash table H equals new, I mean, no, it's hash table is lowercase here. And then we did public HT wrapper, and we pass a hash table. And here, we probably can't say K comma V because we have not really defined them. So then how could we then, oh, I need to import the class hash table. Yeah, there you go. If I did K comma V here, it's gonna immediately say, well, I don't know what K and V is because you are not. Actually, let's even make it as a method, like void set HT wrapper. You know, this is a situation where we are using a generic in a method, but we are not genericizing the class itself. We are just saying, okay, well, you're going to be able just to pass a hash table that has 2 strings for key and value rather than object and object. K and V doesn't necessarily exist here, so we can just put the question, the wildcard thing, and then we can say extends string. Well, like, let's say it's number and number, you know, number and number. But here, because we're using a hash table inside of another object and allowing us to dynamically create that hash table, we can use those question marks to saying, okay, this is how we're going to bound it. Does this part make sense? Okay, then let me.
So Juan, so for that, would you just, if you're doing a method set hash table wrapper, would you just set that hash table that you made to have those types, I guess?
Mm-hmm.
Like H equals some.
Yeah, so for example,
parameters.
if I was going to do, like, you know, this, oh, I need an identifier. So I could do this dot H equals HT. Essentially, I'm reassigning this variable here. But if I did main HT wrapper HTW equals new HT wrapper.
Mm-hmm.
And then we can do HTW dot set HT wrapper, and then we can do new hash table
Mhm.
long, comma, long. And then if I want it, because it's extends from number, I can do integer and then integer and so on. But I cannot go and do this because for whatever reason, my code decided I was only going to accept numbers. You can see that the one from string fails.
Mhm. Yeah.
And it is because of this. We're utilizing the generics again to allow you to do whatever you want with your code, but as long as it makes sense. So for example, if you're writing a calculator and you don't want to have to override every single method with different data types like long. Now I'm going to support long. Oh, now I'm going to support double. You essentially make it generic, but you bound it to just being a number. And then you can play with autoboxing and out-of-boxing to convert from a primitive into one of those wrapper classes.
So Juan, is it like every time you use generics on a method, you have to use like the question mark? Like if you're not specifying it on the class?
Yes,
Or
if I want to bound it, because I could have easily just done this, and now it accepts string and string. It doesn't necessarily care. But if I want to bound it to just be like, okay, I only want a hash table of numbers, then I could use that wildcard to describe what the hash table is going to have. And you see now that we went back into number, this guy string is failing.
Mhm. So if you get rid of that, you can specify when you create the hash table, using that
String,
method,
string.
you can just specify like you don't need to say that parameter hash table is a generic. It just assumes it's going to be.
Yeah, because if you don't specify anything in a generic, the default object is object. Did I explain myself well? I feel like we flew through those concepts. Okay, well, let's maybe get some numbers about generics. Cool. Well, from a hash table, from a generics perspective, yeah, we were, this is another exercise, but once that 10th class was cut out, that gives. I would like then to dedicate whatever extra amount that we have for anybody that has any questions then for the final project or any other pending assignments. So here's what we're gonna do. For those of you that feel like you got it and there's no any issues or anything like that, then class dismissed. It was lovely to teach you guys. I hope you learned something and found this class valuable, despite the circumstances of not being in the same room.